Good morning. This is Michael Goergen from the U.S. Endowment for Forestry and Communities, and I'm here to talk to you about a public-private partnership that we formed with the USDA Forest Service called P3 Nano. Our effort is to try to produce cellulosic nanomaterials into commercial applications that really make a difference, both for forests that are important for all of us, and also to try to commercialize this material that has incredible end-use applications. These nanomaterials are a fifth of the weight of steel, but have all of that strength of steel as well. What's really interesting about them is that we can actually tune them to do things like reflect UV or infrared light. And there are incredible applications that we'll talk about in just a few minutes. But what I want to talk about is how we've been able to reduce the cost for entry and reduce the cost of commercialization of these cellulosic nanomaterials as a public-private partnership. What we've done is we've brought together a number of different organizations, including the Forest Service and the Endowment and other partners. And we looked at a couple of areas where we thought we could bring some real strength to getting more rapid commercialization of these materials. The first thing we looked at was health and safety. We also wanted to look at things like process innovations where we could reduce the cost of producing these materials, and then also find a home for them in end-use products. So let's look at health and safety. First thing we did was we went to the Food and Drug Administration after doing a number of initial tests to prove safety of these materials, and we asked the FDA if we could get generally recognized as safe status for cellulosic nanomaterials. What GRAS status really means is that a material can come into contact with food, or it could actually be part of a food as well. So getting this generally recognized as safe status really matters, because not only will it allow us to have packaging products that could include cellulosic nanomaterials and could actually touch food that we're going to eat, or it could give confidence to other organizations that may be skeptical about using a nanomaterial, but we can showcase and demonstrate the safety of these materials, then people are more open to using them. So we've gone through this FDA process. We've used a reference material. What we've done is created a sort of a generic material. We've recruited several industrial collaborators that work through this process with us, providing both expertise in terms of their science, but also financial support of the public-private partnership. What we've done is, through a reference material, we've been able to just do one set of tests for that material. So instead of each of these companies coming to the Food and Drug Administration and asking them for individual GRAS status for their individual version of cellulosic nanomaterials, if they can demonstrate that their material is similar to the reference material, then they can join and get that generally recognized as safe status for cellulosic nanomaterials as a generic material. So we go through one set of tests, which incredibly reduces the amount of costs of the science end of this. We go through one application process to FDA, again, reducing the cost. So instead of spending millions of dollars per nanomaterial, we spent a couple of $1 million for 8 nanomaterials to get through the process, significantly reducing costs of those organizations and actually opening the door to future organizations to participate as well. And the nice thing for the Food and Drug Administration is that it adds only one review for all those materials as well, which significantly reduces the bureaucracy and the time that's associated with getting that GRAS status through FDA. So they're pretty happy about it as well. Another area that we've been focusing on is reducing the cost of making these cellulosic nanomaterials. In our case, there are a couple of real challenges associated with making them. The first is that it's a very highly intensive water process, so that what we wind up is with a material that's about in solution, about 90% water and about 10% nanomaterials. And shipping water doesn't make a lot of sense, so we need to find ways that we can reduce the amount of water content and then get them a little drier. So we've been working with a lot of collaborators on doing that kind of basic research that really is pre-competitive, but helps reduce the cost of producing these materials. Another example of that is that we can use there's a sulfuric acid that's often used in making these materials. And if we can recover sulfuric acid as part of the process, we can again reduce the costs, because of course we're reusing the material, we're reducing our waste stream, et cetera. And so we've gone through a process to work with multiple collaborators to try to generate a whole recovery of sulfuric acid process, which is pretty exciting, pretty interesting work that's moving forward with our partners at the Forest Service and others. The other area that we've really been focused on is trying to get to end-use applications. And what we found in terms of getting to commercialization faster is that we need to find products that solve problems. This is really critical. We can't just create a gee whiz new application for cellulosic nanomaterials. We've got to find ways that we actually solve industrial problems. We need to make sure that we find ways that they're compatible with existing processes as well. We need to be able to improve performance while reducing the overall costs, and we need to find large markets for these cellulosic nanomaterials, because niche markets are fun and interesting, but the way we're really going to be able to reduce costs and produce volumes of cellulosic nanomaterials is find those large markets. So what have we been up to? Well, we're looking at a number of really exciting different kinds of applications. We can actually work on including cellulosic nanomaterials in various polymers, including biopolymers, so that we can get some of the strength and some of the barrier properties that we can generate by using cellulosic nanomaterials into some of these bioplastics, hopefully reducing the need for petrochemicals in general. We're using them as foams inside of things like structural insulated panels and other materials. And then we're actually also using them in agricultural applications where, for example, with cherries, we actually spray these on in the field, and that prevents cherries from cracking. And cherry cracking is a multi-million-dollar loss for a cherry farmer, so they're very interested in trying to spray these materials on their cherries to prevent that kind of cracking for the future. Just goes through a wash-off process, and we're able to reduce the value of cellulosic, or increase the value of cherries by adding just a little bit of cellulosic nanomaterials. Another exciting end-use application is actually sunscreen. We found that we can tweak these materials so that they can reflect UV light, and reflecting UV light, we can actually put these into a sunscreen. And instead of being a chemical process where your body absorbs a chemical to block UV light, we can actually just put these on the surface of your skin and reflect the light that way. There are various applications that are really exciting for this in addition to sunscreen, because there are all kinds of makeups that require some sort of UV protection, and we can add these cellulosic nanomaterials into those products that serve a number of different purposes as well. So really exciting application that we sort of stumbled upon on the one hand. On the other hand, provides the kinds of volumes that are necessary to get cellulosic nanomaterials into the marketplace. Let me give you a bad example. We actually worked on trying to spin cellulosic nanomaterials into a replacement for fiberglass. Fiberglass, a very ubiquitous substance all over in all sorts of different applications. It's got a significant side down effect, which is that it's quite heavy. And if we could reduce the weight of fiberglass by making it out of cellulosic nanomaterials, then we might have a winning product on our hands. But when we really studied the market, we were able to produce these cellulosic nanofibers. We were able to do it in the lab, no problem. The challenge is that fiberglass is so cheap that it just doesn't make sense to make it out of a cellulosic nanomaterial substitute. So even though we could reduce the weight of a car part by probably 30 to 40%, it really probably doesn't make sense when you look at the overall cost of producing the material. Let me give you a real winner for us, and that's concrete and cellulosic nanomaterials. When we add cellulosic nanocrystals, CNC, we actually increase the hydration of cement significantly. And when we hydrate that cement more, what we're doing is we're actually increasing the strength of the concrete mix. And by increasing that strength, what's interesting is that we can actually wind up reducing the amount of cement that's in concrete. And that reduction in cement reduces the amount of greenhouse gases in concrete overall. And as greenhouse gases from concrete are about 8% of the world's emissions of greenhouse gases, reducing greenhouse gas emissions from cement by about 20% is a real win for the concrete industry. So they're very interested in this. And remember how I told you that these materials are wet? Well, they just mix right into concrete. We don't have to worry about drying them or anything else. They can be put right into a system that already includes water and is a real benefit to that system. So this is an application end use that we've tested. We've gone to the field. We're making here a beam for a bridge that will go into place. This is a precast, pre-stressed beam. Once that dries, we'll be able to put it in place on a bridge deck in Wairika, California. What's interesting about this is that when we really look at the application, we're finding all kinds of need for this from transportation agencies. They've all been tasked with reducing their greenhouse gas emissions, and it's very difficult to do in transportation. But this 20% decrease from concrete is a significant win for them. And if we can show consistent performance of these materials in reducing the greenhouse gas emissions from concrete, we anticipate widespread adoption of these materials. And a state like California that is very interested in this solution, we can see significant potential for volumes, and that volume production of cellulosic nanomaterials will drive the cost down for other industries that are interested in adopting them. Again, so what we're looking for was a big volume opportunity for us so that we could pave the way for other markets to open. And what's interesting about using cellulosic nanomaterials in concrete is that we can make them out of wood, as I had mentioned earlier. And in a state like California that has tremendous wildfire issues, we can actually go out and do the kinds of restoration work in those forests that's needed. And we can take the material out of the woods that might burn up and use that to create these cellulosic nanomaterials. And so when we make concrete, we need about 9 pounds of cellulosic nanomaterials for 5 tons of concrete. And what that really amounts to, if we look at restoration opportunities in the forests of California, that's about 23.65 acres of forest treated for every mile of 4-lane highway. So again, these materials are solving multiple problems. It's creating a market for these restoration materials in these forests. It's reducing greenhouse gas emissions, and it's creating a future where we can put this bridge in place in California and do good for a lot of different industries. Thank you.